Okay, this is notes 11.1 part 3. In the last video I forgot to add this in here. So the overall process for this reaction here that we just did, the overall process for this reaction here, it's negative. That's our delta H. It's negative, and it's exothermic. It's exothermic. Okay. Explain why using the delta H of the reaction. Well, that's what this graph was about. Okay, the delta H of the reaction is negative. Okay, delta H of the reaction equals less than 0. And explain why using the graph. Okay, let's look at the graph one more time. The amount of energy released, okay, when this, the amount of energy needed to form these bonds is greater than the amount of energy needed to break the bonds. Okay, so that results in a negative delta H. So what we can say is this: energy of the products is lower than the energy of the reactants. Okay, the energy of the products is lower than the energy of the reactants. Okay, let's move on to the second part here. And we'll call this enthalpies of formation. We can just, instead of, this is the only time you'll see it listed as enthalpies of formation. What you need to remember is this. It's just the potential energy. Okay, it's potential energy. Okay, potential energy in 1 mole of the substance. So this is the amount of energy stored. Amount of energy and chemical bonds. Right, we all know that gasoline burns. Why does gasoline burn? Why is it so explosive? Well, it's got a lot of potential energy stored between those chemical bonds. Okay, that's why. That's why it's explosive. That's why we can use it to fuel our cars. Okay, because there's a lot of potential energy stored between those bonds. So that's what we're talking about, and we're going to represent this as H sub F. Again, this right here just means potential energy. And if you want to say it like this, potential chemical energy. Now the potential energies of these substances have been calculated and tabulated. Okay, O2, because it's bonded to itself and because it's a pure substance, it's got a potential energy of 0. Okay, but the rest of these compounds have been measured, okay, throughout the years, and you can find these in tables in the back of chemistry books and online, etc. And it'll tell you how many kilojoules per mole of potential kinetic energy, of potential chemical energy, are stored between these bonds. And so what you can do is, instead of calculating how much energy each bond requires to break or releases, you can just look at this thing right here and use it to figure out how much energy is released or absorbed throughout the entire reaction. So I'll show you how that's done. It's actually easier than the way we were doing it before. Consider the equation for the combustion of methane, CH4, and there it is, balanced. Calculate the, instead of enthalpy of products, we'll say potential energy. Potential energy. Okay, just instead of enthalpy, just say potential energy. Potential energy. Okay, it's easier to think about it like that. Okay, so here's how you do this. Of the products first, so we've got 1 CO2, 1 potential energy of CO2 plus 2 potential energies. That's what this HF is, H sub F, of H2O. So all we're doing is we're just taking this number here, okay? CO2 is negative 393 kilojoules per mole, H2O 286 kilojoules per mole negative, okay? And then we're multiplying out how many moles of this stuff we used. or how many moles were formed rather. So we get 1 times negative 393 plus, just substitute these numbers in, that's all I'm doing, 2 times negative 286. Okay, when you do that math, I ran out of room, but when you do that math in your calculator, you get negative 965 kilojoules per mole. Okay, you get that. All we did here, you guys, all we did here was what we just did back here. Okay, we did the same thing we did over here. It's just that instead of counting the bonds individually, we use the potential energy. That's all. So our potential energy of our products is going to be negative 965 kilojoules per mole. And let's go ahead and count out the okay, sorry, let's go ahead and do the one calculate the total potential energy for the products. I'm sorry, for the reactants. Okay, so we've got CH4, we've got 1 times the potential energy of CH4, which is negative 75 kilojoules per mole, plus 2 times O2, which is 0. Okay, that's a grand total of negative 75 kJ per mole. Okay. So calculate the delta H of the reaction. So here's how delta H of reaction, that's the formula for it. Delta H of the reaction is total potential energy of products minus total potential energy of reactants. Okay, so let's do that. Negative 75, sorry, negative 965 kilojoules per mole minus negative 75, right, kilojoules per mole, because that's the potential energy of the reactants. Okay, I'm following this formula right here. So negative times negative is a positive, and that's going to be negative 965 plus, remember that's a positive, 75 for a grand total of negative 890.5 kJ per mole. Now if you've been really paying attention, you go, well, wait a second, Mr. Medeiros, that's negative 890 for this reaction, and just a second ago we calculated using the bond energies, we calculated negative 716 kilojoules per mole. What gives? Did you screw up again? No, I didn't screw up again, believe it or not. This is actually more accurate, okay, and we're going to address that down here. Okay, if they are not the same, why are they different, and which is more accurate? Okay, because whenever we calculate bond energy, I'll just tell you now, when we do these calculations using bond energies, this is an average. Okay, this is the average bond energy, so it's less accurate. Okay, so what you can say is the bond energy method uses average bond energies, not actual bond energies, so it's less accurate. Okay, bond energy method uses average energies. So it is less accurate than what we just did, as a matter of fact. Even though this seems it's easier, right, because the numbers are already calculated for you. So you might think that this is less accurate, but it's not. Oops. Okay, let's plot the energies of the reactants and the products on the graph to the right and show the delta H of the reaction found on the graph. Okay, so the energies of the products and the reactants. So let's look at the reactants. The potential energies of the reactants: CH4 plus 2OH, and we said it's roughly negative 75 kilojoules per mole. So that's a negative 100, that's negative 200. So we got to plot it in this direction, right? Notice that's 0. Our graph is going in the opposite direction, right? Even though the arrow is pointing upward. Okay, we start at 0, we're going in the negative direction. So negative 75 is going to be over here somewhere. So we can say that's going to be CH4 plus O2. Okay, right around there. I'm just going to go ahead and put it on 100 just because it's easier. We got a line there. Okay, and then our products are CO2 and H2O, and we said they're at negative, they're at negative 965. Okay, negative 965, so they're going to be right in here somewhere. These are our products, and that's going to be CO2 and water. H2O, okay, and again, this right here, this difference in potential energies is our delta H of reaction, okay? So there's that. The overall process for this reaction is exothermic. Explain why using delta H of the reaction, simply because delta H is less than 0. Explain why using the graph. Energy of, we can just say energy was released. Now we can say energy of products was lower than energy of reactants. Because energy is released, it is a product in the thermochemical reaction. Write the thermochemical equation here. Well, it looks like this. CH4 plus 2O2. This is gas, and gas yields carbon dioxide plus H2O, gas, and liquid, although that's really gas, but alright. We can say liquid. Plus what else, you guys? Plus heat. Right? How much heat? 0.5 kilojoules of heat is released. That's per mole now, per mole of this reaction, okay? So there you have that. If heat is a product, remember from first semester, if heat is a product, then this thing is exothermic, and we've just demonstrated why that is, okay? Because the amount of energy that was released when these new bonds formed was greater than the amount of energy that we put into this reaction to break the bonds. That, my friends, is the takeaway. Okay, please listen to that again if you don't understand or if it didn't sink in. Okay, and that does it for the final video of 11.1 notes. I'm going to go ahead and make a solutions video for the 11.1 worksheet.